It's Dr. Gilchrist, and since I am going to be in Chicago and coming back from Chicago on Tuesday, we're obviously not going to be having class, so I want to make sure that I spend a little time finishing up our discussion of correlations. When we come back from our Thanksgiving break, we will start talking about chi-square tests and frequencies, and then we'll finish up by talking about one-way independent variable designs. So let's go ahead and begin. We'll pick up where we left off last time. We talked about the importance of scatter plots, how to calculate Pearson's R, what this would look like in ESCI. And now we're going to move on to talking about how we actually get a confidence interval on Pearson's R. Remember that for any type of inferential statistic, whether it is, you can go away, Zoom, why did you do that then? No matter what type of inferential statistic we're talking about, whether it is an ANOVA test, whether it is a confidence interval or a t-test or Cohen's d, we need to actually determine a confidence interval. So we're going to start by talking about the confidence interval on R and the dance of Pearson's R. All right, so this actually comes from table 11.1 in your book. Basically, what is being done here, this is a case where we're looking at a data set that's basically random samples from a population. We are going to assume it's really large. So this data actually comes from a row, a population with a row of 50 with 50 different samples of number of people or data points, those XY pairs of 10 and then 40 and then 160. And so remember that this is an underlying population correlation coefficient of 50. And what I want you to kind of pay attention to here is that when you have a small number of XY pairs, such as 10, notice how widely our correlation coefficient swings. As we increase the number of XY pairs drawn from the population and sampled, we get something that is closer to the original estimate. So notice that here we do get an average that's pretty close to about 0.5, but notice here that it comes out to about 0.46. That's a little bit off. Here, again, we've got some variability, but as we get more people drawn from our sample, you're going to see that we're hitting closer and closer on that true population value. And notice that our standard deviation has considerably gotten smaller as well. So just like with confidence intervals and with p-values, our values will also have a dance. So the correlation coefficients are also subject to this dance. So the data here is corresponding to a row of 0.5. Just as a reminder, row is Greek. This looks very different from P, which should be italicized as in p-value. Population estimates like row are never italicized. Sample statistics always are. Now, because of sampling variability, remember, we're always sampling from a larger population, and that sample is not always going to accurately reflect the population that we draw from. So the R values are going to dance around. The smaller our n is, the more that we are going to see those variability swing. So notice that our correlation coefficient can be as high as 0.78 and as low as negative 0.13. So we've got a lot of variability there. But as our n gets larger, the less variability we see. And that's accurately reflected by the decrease in our standard deviation. Standard deviations are a measure of spread here, and you can see that as our n gets bigger, our standard deviation decreases. There is much greater variation for an n of 10 than for an n of 160. So because of this variability, we need to have a confidence interval on R. So how are we going to do this? So R is basically going to function as our point estimate of rho. just as our sample mean is basically functioning as our point estimate of mu in the population. So we can actually use R to estimate rho. So we have to have a couple of different assumptions here. So first of all, we need to assume that our data comes from a random sample from a large population of XY data pairs. Now here's what's really critical. X and Y both need to be normally distributed. So this is what we call a bivariate normal distribution. Bivariate here means that we have two different variables. We have X and we have Y. So what you're looking at here is a scatter plot for a large sample. This is about 5,000 different data points. And you can see that in panel B, you can actually see the distributions of Y at two different values of X. And you can also see the, so here you can see the distribution of Y for a given X. Here's another X, and you can see that that is also normally distributed. And then here at this given value of Y, we can actually see the distribution on X. So a bivariate normal distribution is basically going to function like a smooth hill. It's going to be kind of flat on top, and ultimately we're going to get an ellipsoid shape that kind of looks like this. So if we choose a single value of X, such as right here, the distribution of Y at that X should be normally distributed. And the same will be true if we are choosing one value of Y for X. Now, generally, it's going to be pretty safe for us to assume that our data is a random sample from a bivariate normal population, but we are going to have some exceptions. So this would be the case if we already know that we are dealing with a nonlinear relationship, such as we saw between room temperature and comfort, where it kind of made a parabolic shape like a parabola. It could also be that we would have an exception to this if our scatter plot shows signs of a nonlinear relationship. And additionally, if we don't think that our data set is actively coming from a larger population. So these would be the few times that we can't make this assumption, and we may not be able to calculate a confidence interval on R. So ESCI, as I kind of showed you last time, can actually do this for us. If we're willing to meet both of those assumptions, that it comes from a random sample with a bivariate normal population, we can use ESCI to calculate the difference. I am not the confidence interval, rather, and I'm not actually going to have you calculate this yourself. It's a little bit too complicated. So again, let's just go into ESCI very briefly so that you can see this confidence interval being calculated. So we're going to go into our ESCI files here. We're going to go into chapters 10 through 16. I am again going to go into our scatter plots tab, and I'll show you exactly where you can get the confidence interval for this correlation. So if you are doing this for the homework assignment, for the confidence interval, you are going to need ESCI. If you can't get ESCI, get somebody in the class who has ESCI to help you. You don't even need to give me an ESCI printout, just get the actual measure from a classmate and you'll be good to go. So we're going to go ahead and enable content. We're going to go to scatter plots. So here is our Thomason data. Again, I'm going to show you the z-scores, and you can actually see that without showing the z-scores, just by entering in this data, in our area right here, in our number 7, you can actually see the confidence interval on R. So the R that was developed in our sample is 0.89. The actual true value, assuming these assumptions have been met, is that the actual population correlation coefficient is ranging between 0.65 and 0.97 with 95% confidence. So if you had this data on hand, what I would want you to do is actually report the confidence interval on your correlation coefficient, like you should with any sort of statistic. So you can actually use ESCI to help develop and determine the confidence interval. So we're going to once again look at this in a very different way. And you're going to see, we go to one correlation. You can actually display a cat's eye picture. So here we have a correlation in the population of 0.4. I'm going to go ahead and change this so that it fits with the Thomason data, if I can. 17, 16, 15, 14, 13, 12. I don't think, oh, we can change it here. So the correlation that we obtained for the Thomason data was 0.89. So I'm just going to move. Oh, wow, that's terrifying, isn't it? Okay, so we're so close here. We're going to drop it down to 8.9. I'm going to go ahead and get this to 0.75 so you can see everything. So you can see right here, here's our correlation coefficient that we obtained from Thomason, which is right here with 12 XY pairs. So you can actually see that there is a bit of asymmetry here. Notice that the cat's eye picture and the confidence interval on R, as you can kind of see here, is actually much longer towards the lower end of that range. The more likely values in that cat's eye picture is really kind of highest around the point estimate, and we can actually display our p-value and the p-value for rho for this. So as you can kind of see here, there is some asymmetry, and you can also see this in that tab on ESCI. Generally, our upper margin of error is going to be smaller than the lower margin of error as it stretches towards 1. So we're going to get that compression. That's especially obvious here when our correlation coefficient is already ridiculously close to 1. And because it can't get any higher than 1, we're going to see a longer margin of error. And you can see how symmetric that is. Asymmetric that is, the closer that we get to that 1. So what you're looking at here is what was originally on ESCI. So the cat's eye picture is displayed. The null hypothesis is that there is a correlation coefficient of 0 in this case, and the p-value for that is actually shown there as well. So this would correspond with a p-value of 0.028, suggesting that this correlation coefficient is statistically significant. So here's another way to kind of visualize this asymmetry. And so what you're looking at here are different confidence intervals on R. So here we have basically an R of 0. Remember that this ranges from +1 to -1. And you can see that as the correlation coefficients get closer and closer to 1, the further R gets from 0, the confidence interval gets shorter, and it also gets more asymmetric. The side that is furthest from 0 will be the smallest side. So this is, you can kind of see the asymmetry. It's perfectly symmetrical at 0, but the more that we move away from it, the more asymmetrical it gets. Likewise, here you are looking at the effect of sample size on those confidence intervals. So generally, here is an R of 0 with sample sizes of 10, 40, 160, and 640. In general, the more people that we have, the smaller our confidence interval becomes. Here's the asymmetry for about 0.8 and -0.8. And once again, the larger that our sample size is, the smaller that this confidence interval becomes. So this is for a correlation of -0.5. This is for 0.8. So sorry if I misspoke. That is not -0.8. Okay, so if you want to plan a correlational study, this can be complicated because your confidence interval length not only depends on your correlation coefficient, it depends on the number of people. In fact, it's complicated enough that you are not expected to figure this out on your own. Figure 11.19 in your book can actually be pretty useful for this. So for correlations that range between or are expected to range between negative 0.5 and 0.5, make sure that you have over 100 people, or for a margin of error of 0.2, or if you want a margin of error that's less than 0.1, you're going to need over 300 people. So now we have to talk about how to interpret correlations, and y'all know what's coming. We have to talk about the fact that correlation does not imply causation. So if X and Y are correlated, there may be a causal link, but the scatter plot can't actually tell us what they are, and there are several possibilities. So it could be that X causes Y or Y causes X, and we can't determine which is which with the data that we have. It could be that one or more other variables play a role in causation. Additionally, it could be that we could be seeing a face in the clouds. So your book talks about the fact that from 1999 to 2009, there is a 0.95 correlation between oil imports in the United States from Norway and the annual numbers of drivers in the US who die in train collisions. So this is another kind of spurious correlation that we've talked about in the past. It's entirely possible that this is a case where we have no underlying cause to be found. It's just a weird, spurious correlation. So here's another example. We do actually find that parental adolescent drug use has been reported to increase after divorce. Now, it's possible that this could be that parental divorce leads to adolescent drug use, or children use drugs, and oftentimes what we're going to find is that it rips families apart. My stepbrother had some drug use issues growing up that actually kind of tore apart my family and led to a divorce. But they could be due to something else altogether, like living in poverty. So researchers do note that there is a tendency for children of divorced parents to use drugs more than in intact families, but drug use could cause marital problems. So there are some other things that could be due here. So be very careful assuming that there is a cause-effect link between variables that are correlated. And I would urge you to think of examples of your own where it's very difficult to figure out what that cause is. So when we're interpreting values of R, just as with Cohen's D, there are actually reference values for R, but they vary. And generally, you want to have a sufficient context before you make a judgment. Figure out what's common for your field and with people who are doing research in your area. Now, Cohen suggested 0.1 for a small correlation, 0.3, and 0.5 for medium and large correlations, respectively. We can also use correlations to measure reliability and validity. So one of the things that we can do if we want to figure out if a test that we are using is a reliable measure, we can actually see how well it correlates with itself. So you may have a group of people all take a new test twice and see how they correlate from day to day. Retest reliability on well-established tests should be a Pearson's R of 0.9 or higher. If we want to look at validity, we may want to correlate a new measure with older measures. And ideally, if they're looking at the same thing, they should be hanging together. They should be pretty highly correlated with each other. And what we will often find is that for validity on well-established tests, it's going to be as high as an R of 0.8 or of 0.9. So when we're using R to judge reliability and validity, you should consider an R of 0.8 or 0.9 good. And if it's 0.6 or 0.7, it is not good enough. Generally, compare it to other reference values, other research studies in your field, and remember that context matters. Now, I want to go back to the confidence interval on the difference for R. So I want us to go back to looking at the relationship between body satisfaction and well-being. So let's say we wanted to look at whether this relationship holds when we divide people by their self-reported gender. So looking at people who identify as men, people who identify as women. So if we looked at these two scatter plots, imagine we found something like this. We get a 0.53 correlation for a group of 47 people that identify as male, and a 0.41 correlation for 59 people that identify as women. So is it really true with this data that men have a stronger correlation? And in this case, we would need to get the confidence interval on the difference to know for sure. So again, we're going to do this in ESKI. This is not, so when we want to compare two different correlations, we would want to look at the confidence interval for the difference. So here, let's go ahead and take a look in ESKI. And thankfully, we are almost done with this. And again, I would not expect you to do this by hand. ESKI can do this for you. So here is our data. So we have, let me take a look. Okay, so we have 47 men. So R2 is our correlation coefficient for people that identify as male. Our correlation 1 is for people that identify as female. So you can kind of see, here's the correlation for our male group, here's the correlation for our female group, and you can see the confidence intervals for both of these things. So you can see that the correlation for our female participants basically ranges between 1.72 all the way to 0.63. So this is a pretty broad correlation. Here is our correlation and our confidence interval on R for our male group. You can see that that also ranges from 0.28 all the way up to 0.71. And again, you can kind of see the asymmetry in our confidence intervals. When we're calculating the difference with 95% confidence, so we're subtracting the difference from R2, our male group, minus R1, our female group, our confidence interval on the difference is actually pretty broad. In fact, it's broader than either correlation on its own. And you can see that 0 is included in this confidence interval, as is a negative correlation and a positive correlation. So the confidence interval actually ranges between negative 0.19 and 0.4. If we had a p-value that actually shows this, the p-value is 0.44, indicating that this is not significant at all. And we can actually mark the overlap here. And you can see there's pretty significant overlap between these groups, indicating that there's probably not actually a difference in the correlation between satisfaction and well-being between men and women. So let's go back here. So when we're doing this in ESKI, what we basically see is that men don't necessarily have a stronger correlation. Both of these confidence intervals are incredibly long, which means that our difference axis reflects that uncertainty, and there probably actually is not a difference between our male and female participants. Now, we can also do this with meta-analysis. So if you've had me for cognitive psychology, you have heard me talk a little bit about deliberate practice and its role in developing expertise. Brooke McNamara and colleagues actually ended up doing a meta-analysis back in 2014 to determine if that expertise is actually based on time spent practicing. So let me see, we can't actually report that here, but you can actually look at this data in ESKI, and it's in single R in that intro to meta-analysis. So I can show you that another time if you'd like, but it's very similar to what we talked about in the meta-analysis section before. So if we open up our ESKI files, you can actually kind of see this right here. So we go into our meta-analysis file, and we're going to go to wait, this is not the one we wanted. We wanted the other one, and it's taking its sweet time to load. There it is. Okay, so we're going to enable editing, and we are going to enable content once it loads. There we go. And we're going to go to one that's called single R. So here is the McNamara data. I'm going to go ahead and show the p-values as well. So here we have a meta-analysis where we have different types of musicians, and we're basically looking at the correlation between the amount that they practice and their performance levels. And so what you're kind of seeing here, and you can actually see the forest plot here and the result of the meta-analysis using random effects, that there does seem to be some correlation between practicing, amount of time spent practicing, and proficiency. So here's what we kind of see. So a lot of the work on deliberate practice comes from the work of the late Anders Ericsson, who basically reported that about years of effort and 10,000 hours or 10 years, give or take, he developed that with Herb Simon, the amount of time spent practicing matters most. And so McNamara found basically that there is a correlation of about 0.41, which is right here in the random effects, ranging between 0.28 and 0.53 between practice and achievement in music. And if we're looking at all fields, such as chess, such as sports and athletics, it's actually closer to 0.35. So here's what's kind of clear. Effort matters. The amount of practice matters. But notice that this is a pretty small correlation, indicating that there's some other stuff going on here that might also lead to the development of expertise and proficiency. So in many fields, the correlation between the amount of practice and achievement is not bad. It's a medium correlation, but if it only took practice, we would get a much stronger correlation here. So you can actually use the power of meta-analysis to figure out findings from different studies that look at correlations. And this can tell us something really meaningful. So folks, this is pretty much all I had for correlation coefficients. Use ESCI, or I would say for the homework assignment, since you are expected to calculate the confidence intervals, go ahead and use ESCI or talk to somebody in class who has ESCI, and let me know if you have any questions. I will be back after break, and we will start talking about, we'll start to talk about chi-squares and frequencies. Have a great day, and I will see you next time.